So, as you may have remembered, I promised you that I would never miss another day. I am a horrible liar, if you haven't already figured that out. I'm just gone for a day. I am doing a quick little workshop about how to design cross-curricular projects. Nothing you guys need to worry about. I'll be back on Friday, when you guys will next be in my class. So, all you guys got to worry about is what we're doing today. Really easy class for you guys today. We're going to do a bunch of example problems on waves. These are old AP problems, ones that I have chosen because they are very similar to what's going to be on the new AP. And then you're going to start designing your instrument in class, as in drawing things and getting numbers and doing calculations. Let's go ahead and get started. Which of the following statements about the speed of waves on a string are true? 1. The speed depends on the tension. The speed depends on the frequency. The speed depends on the mass per unit length of the string. Alright, well, speed of a wave on a string. You have a few different equations here. Hopefully you guys at this point already have an answer. Here's how I would do this, though. I got that equation, which tells me that there is a relationship between frequency and speed. But hopefully you remember that speed is only dependent upon the medium. So, I'm going to say that that's not possible. If you're lucky, you also happen to remember that you have an exact equation for the speed of a wave on a string, which is the square root of the tension force divided by the linear density. So this gives us the answer of C. Hopefully you agree with me. Next problem. Oh, in case you haven't figured it out, you're trying to beat me to the answer, which is really easy since I'm a video. So you can read the problem, pause it, do it with your group, hit play again, and listen to my explanation. Works out really nicely. Alright, so here we got a picture of strings firmly attached at both ends. When a frequency of 60 Hz is applied, the string vibrates in the standing wave pattern shown. Alright. Assume the tension in the string and its mass per unit length do not change. Both those things are fairly good things to assume. Which of the following frequencies could not possibly produce this standing wave? Oh, produce a standing wave, not this standing wave. Alright, I was confused because of that. Alright, so, let's see. You're pausing. You're doing the problem. You've now hit play again, and you're going to hear my explanation. There's a node, there's a node, there's a node, there's a node, which means the harmonic number of this is 3, being n minus 1, number of nodes minus 1. Alright, so I know that n equals 3. I know that the frequency of this third harmonic is 60 Hertz. Which of these could not also produce a standing wave? Well, I know that all of my frequencies have to be a factor of my fundamental frequency. I know my fundamental frequency, using this, divided by 3. What is 60 divided by 3? Let's see. Well, 6 divided by 3 is 2, so 20 Hertz. My question is, which of these is not a multiple of 20 Hertz? 180, that's a multiple of 20. 100, multiple of 20. 80, multiple of 20. 40, multiple of 20. 30, not a multiple of 20. So since my question is could not, the answer is A. Huzzah! Moving on. Which of the following is not associated with the sound wave? Sorry, I had trouble just reading that for a second. Amplitude, period, polarization, velocity, wavelength. Well, this one's nice and easy, because I've told you about all of these things except for one, so chances are it's not that one. Moving on. Alright, another standing wave pattern. This time it's of n equals 4. So before I read the problem, I'm going to recognize that. The standing wave pattern diagram to the right is produced in a string fixed at both ends. The speed of the wave in the string is 2 meters per second. What is the frequency of the standing wave pattern? Pause. All right, you just hit play. Let's hear the explanation. Speed of the wave in the string is 2 meters per second. N equals 4. What is the frequency of the standing wave pattern? Oh, well, we need to know the relationship between wavelength and length. Because I know the length is 1 meter. Oh, what is that relationship? It's something like wavelength, and there's an N in there, and there's an L in there somewhere, and isn't there a 2 in there somewhere too, as well? So, if only I had an equation sheet, and then I could look this up. Gee, how convenient. So this one's pretty easy. You just, literally look at the equation, and you plug it all in, and you get yourself an answer. So since the equation is right, I want frequency. Well, I could do it this way, and then I could say frequency. That would probably be the most direct way. So wavelength is going to be 2 times L, which is 2 over 4. So what's 2 over 4? Well, that's 1/2. So I have a speed of 2 equals 1/2 frequency. Chances are my frequency is 4 hertz. Let's see, can I math? I can. Next. String L and string H have the same tension and length. String L has mass m, and string H has 4m. If the speed of the waves in string L is v, the speed in the wave is what? Tension force is the same. Length is the same, but the mass is 4 times greater, so v4. Interesting. So that means that VH is going to be square root of 1/4 gives me 1/2. So let's see if I did it right. Yay! Next. How many of these are there, Mr. Saslow? 5 bajillion. Moving on. When a train is at rest, both the passenger on the train and the ticket seller at the station agree that the train's whistle produces a sound of frequency 120 hertz. When the train is moving away from the station at 50 meters per second, the passenger hears a frequency of blah, and the ticket seller hears a frequency of blah. Okay. Passengers are on the train. Ticket seller is not. So I can figure out this first number immediately. If the passenger is moving at the exact same speed the train is, it should be hearing 120 hertz still. Okay? Which means that's a possibility. This is not. That's a possibility. This is not. And that's a possibility. The ticket seller hears a frequency of blah hertz. Alright, well, should it be a higher number or a lower number? They're moving away, so it should be a lower number. So that's a possibility. This is not. This is a possibility. Oh, sorry, no. What am I talking about? That's not a possibility. Bam, cross-elimination, no math necessary. Answer's correct. Next. See, only 5,000 bajillion minus 1 more left. Words are hard. A pipe that is closed at one end and open at the other resonates at the fundamental frequency of 240 hertz. The next lowest/highest frequency it resonates at is most nearly... What is this next lowest highest thing? I'm thinking closest. Alright, you do it. Yay. Okay, now I'm going to explain it. If the fundamental frequency is 240 hertz, if you recall, all subsequent harmonic frequencies have to be multiples of it. Is 60 a multiple of 240? No, it is not. Is 80? No, it is not. Is 120? No, it is not. Is 480? Yes, it is. Is 720? I'm going to have to do math? Okay, well, even without doing any math, I know that it's going to be one of these two. So, is this a multiple? Shoot, I don't know. It's late. I'm sleepy. So let's see. 720 divided by 240 is in fact a multiple. Okay, so it's going to be, this is n equals 3, and this is n equals 2. So the answer is going to be n equals 2. What? But Mr. Saslow, I don't understand. What happened? Well, if you remember about our equations for a closed-ended pipe, since things are kind of funky and strange, you have an antinode here and a node here, you only use odd ends. So, it can't be that one. Fun question. Good work. Good work. Next. Questions 15, 16. A natural horn, which is a trumpet with no valves, just a length of tube, basically, that you vibrate your lips at one end. Similar to a pipe open at both ends. A musician plans to create a fundamental frequency of 256 hertz, which we call middle C, except that's a lie. In our scale of A equals 440 hertz, middle C is not 256, so this is a different scale. But any case, we don't care about that right now. Using the horn. 15. If the sound travels at 350 meters per second, what must be the length of this horn? What? They're giving me speed and they're asking me for length? But I know frequency. Have you figured it out? We need to know the wavelength to length equation relationship for an open-ended pipe. Alright, so you get that it's, oh hey, look at that, the exact same relationship as for a string with both ends fixed. Because you got an antinode to an antinode, where on a string, it's a node to a node, so the distances end up working out the same. That means L equals... Nah, I don't want to do L equals, I want to do wavelength equals. Wavelength equals 2L over N. Alright, fundamental frequency means that N equals 1, so I don't need to worry about that. Wavelength equals 2L. So I need to know my wavelength. Okay, well, I know my frequency, I know my speed, I can solve for my wavelength, which I can then divide by 2 to get the length of the horn necessary. Bam. Oh, man, I revealed that. Pretend that didn't happen. Alright, talented musician can produce a number of overtones. An overtone is those different ends. So n equals 1 is your fundamental, but n equals 2 plus are called harmonics, or overtones. Ooh. What would be the frequency of the fourth overtone? And the musician is playing this exact horn. So we just solved for the length. We have that. What's the fourth overtone? It should just be that times 4. Done. Moving on. Tube of length L1 is open at both ends, so you got an antinode and antinode. Second tube of length L2 is closed at one end and open at the other, so you got antinode node. The second tube resonates at the same fundamental frequency as the first tube. What is the value of L2? Okay, well. Remember that this one is going to be, if we rearrange it, didn't rearrange it. There you go. And wavelength over 2. Okay. Where, same fundamental frequency, so we don't care about n because it's 1. Alright, wavelength over 2. Where this one is, if you recall, 1 only works for odd ends, but since we're at n equals 1, that's odd, so it works just fine. What is the denominator here? Yeah. So that's going to be wavelength over 2 times 1/2, right? So I'm going to say, bam. Small vibrating object X moves across the surface of a ripple tank, producing wavefronts as shown above. The wave moves forward. Doppler effect. All right. The object traveling in what direction and with what speed relative to the speed of the wave fronts produced. All right. So look at the wave fronts produced. What direction do you suppose dot S is moving? Is it going that way, or is it going that way? Yay! Less than the speed of sound. Good job, us. Standing wave, frequency 5 hertz, set up on a string, blah. So, you should be able to do this one. I'm just going to review the answers. Did you do it right? Oh, good. Alright, transverse wave traveling to the right. That's important. At a particular instant of time, the period of the wave is 0.2 seconds. What is the amplitude of the wave? What is the speed of the wave? Hopefully you should be able to do this using our wave equations. Did you do it right? Challenge question. What's the equation for this wave? Okay, well that's going to be sine. Let's see, that's 2 pi times frequency t. The period is 0.2, which means the frequency is 5. Ooh. It's going to the right, minus. That's going to be 2 pi over wavelength, where half a wavelength is 5 centimeters. So that's going to be a total wavelength of 10 centimeters, which is 0.1 meters. So 0.1 times 2 equals 0.2. I'm sorry, I am not doing math correctly. It's 2 pi over wavelength. So if my wavelength is 0.1, I need to do 2 over 0.1. So 20 pi x. Good. There we go. Hopefully you got some good practice out of that. Even if you don't understand some of those problems, you got something out of it. Please write down all of your questions. Be detailed. So that on Friday, the very first thing we can do is talk about those problems and go over them in detail. Now, to design your instrument, you need to choose if it's going to be an open pipe, a closed pipe, or a string. These 3 categories encompasses every single instrument, acoustic instrument, in existence. An open pipe, that would be something like that. That's going to be all woodwinds and brass instruments. Closed pipe, that's going to be most percussion instruments. So, like a drum, you hit this bit, the bottom of the drum is open, or a xylophone, or any of those other type of phones. And a string, hopefully you know about that one already, That would be your stringed instruments. That'd be your guitar, or cello, or viola, or your double bass, personal favorite. So on and so forth, whatever. Choose a type of instrument. Choose some real instrument as inspiration. Then make me something completely of your own out of non-musical instrument parts. It must play a scale where the notes belong to the A440 Hertz scale. An extra credit if you can play a recognizable song on it, so that does not mean a song that you wrote, but a really real song. For instance, Mary had a little lamb would be a perfect example of a recognizable song that you should be able to play on your made-up instrument. Mr. Cecil, when is this due? Don't worry about that right now. It's going to be due, well, let's see, your test is the end of next week. It's going to be at least an additional week after that. So, just start working. Remember, you need to have a picture and a scale and math. That is your goal for today. Go.